Basic hydrolysis of esters is known as saponification. So what I want to do is I want to look at the mechanism with you, and then I want to look at the second part of the sentence that addresses equilibrium. So let's take a look over here at the mechanism. Well, we're going to start off here with an ester, right? It's the hydrolysis of an ester. So we'll do this. Okay. Now, the first few steps are in equilibrium, and what we're going to add here is water and hydroxide. So the first thing that's going to happen here is we're going to come around and we're going to grab that carbon, because that's where our delta plus is, right? Now that's going to give us our R. There's our carbon here. That's going to be connected to an oxygen, the minus charge, an OR group, and then an OH group that's been added there, right? Now remember, that's your tetrahedral intermediate. So there's that electron pressure, as we've seen before, from that oxygen that wants to have these electrons come back down and reform that carbon-oxygen double bond there. Now when that happens, you're going to kick off the alkoxide OR minus. So we're going to get here our R group, and then there is our reformed carbonyl, and then we're going to have an OH down here, okay, and then plus, right, RO minus. So then the next step of this reaction is not a reversible step. So here we're going to use OH minus. You could also use RO minus, but we're going to use a base. Now we have a lot of hydroxide in solution, so we'll just use that. Now, once that acid forms, you can't have that H hanging out there because this is a carboxylic acid, right? So that cannot exist in a basic solution. So this is going to swing around and grab that H, and then we're going to do that. So that'll give us our carbonyl and our O minus, right? And then we'll just write down here plus resonance. So we know that that will be there, right? And then also H2O. So I want to look at that last step with you guys for a second and talk about why this reaction is not really in equilibrium. So once you form that carboxylic acid, that last step, right, pulls the product over to form this, right? So what we see here is just a little, let's make this a little side note. Right, if we think back to, this is a long time ago, but if you think back to chapter 1, when we talked about acids and bases, right, we saw that you could take something like a carboxylic acid, and here let's add an RO minus. And the question is, how much in equilibrium is that reaction? Right, that's this step right here that we're looking at, right? Well, we know that we're going to form here RCOO minus, the carboxylate. And then we will also form the alcohol ROH. So then if we look at pKa's here, then of course it varies a little, right? But the general kind of target area of a pK of a carboxylic acid is around 4.8. That's acetic acid, 4.74, I think. So then we look on our product side, pKa here is equal to, and again it ranges a little bit, we'll call it 16. So depending on what alcohol and what specific carboxylic acid, those numbers are going to vary a little bit, but it's not going to make a difference in our point. So then let's look at our KEQ, and we're going to do this in the next chapter. We're going to have to know this. So KEQ for this is equal to 10 raised to the difference of the pKa of our product acid minus the pKa of our reactant acid. So here the pKa will be 4.8 and 16, so then the KQ is 16 minus 4.8. Right, so you get 10 to the 11.2. So that's greater than 1,000. So this reaction is really, if we're putting in reversible errors, it's really like this, right? So we're greatly favoring our products here. So that saponification reaction refers also to the process of making soap. So somewhere around 500 BC, it was found that taking animal fat and treating it with ashes, like from burnt wood and stuff, produced a soapy substance. And in the ash from the wood, there were probably hydroxides and other bases that would do this hydrolysis. So I want to talk to you guys for a second about soap. So let's take a look at the reaction here. So first we're going to draw out a fatty acid. So this is the general structure of a triacyl glyceride. So here we'll call this, animal fat, essentially. Now, our chains off of here are going to have a different number of carbons depending on what source of animal fat you have, so it doesn't really matter. So let's just build those up to have about that number of carbons. All right, and then we'll just complete that down for the next ones too. So, and don't get caught up too much in the exact number there, but let's put those in. All right, now, often that's a total even number of carbons when you count off the carbons from the carbonyl out. All right, so then what happens is this in the course of this reaction. So what we're going to do here is we're going to take this and we're going to add excess sodium hydroxide. So Na plus OH minus here. Now what we're going to get is we're going to get this part of the molecule coming off and that part of the molecule, right, coming off too. So there's three of them, so it'll be three separate pieces. So what we're going to get here is the alcohol part, which is CH2OH, right? So that's your carbon backbone of that fat, right? So these are all going to become OHs. And then we're going to get the sodium ion, of course, that's in there too. But we're going to get three of these side chains. So oxygen minus charge, carbonyl, and right, with our carbon chain looking like that, right? And then, of course, you got sodium ions floating around in solution. So these are our two products that we get here. Now, let's look at both of them a little bit closer. So when we look at this molecule, if we try to classify this as being polar versus non-polar, well, we have to consider two parts. So there's this head part, and then there's this tail part here. So that tail part is definitely non-polar. So non-polar things we say are hydrophobic. That's a shorthand notation for hydrophobic. This group over here is polar, and polar groups like water, so we call it a hydrophilic, right? Little heart there for hydrophilic. So we're going to talk about how this organizes itself in a solvent like water in a second. What I want to do though is I want to look at this molecule. So the name of this molecule is 1,2,3 propane triol. It goes typically by its common name, which is glycerol. So it turns out that, that glycerol can undergo a further useful reaction. So it turns out that during World War II, that there were posters in grocery stores that looked like this. So it says, "Save waste fats for explosives." And our grandparents or great-grandparents would cook, and when they were done with their fat, they'd keep it in a little jar or something, and then they would return it to the butcher. And the butcher then would put it in big drums, and the government would come by and pick it up. So why is that? Well, let's take a look. So they took the animal fat and they did hydrolysis to make glycerol. Now glycerol, and we're going to come over here, can become nitrated. So with HNO3 and H2SO4, we can make the following molecule. So I'm going to write this thing out here. So here's our CH2, here's our CH, and our CH2. So that's just the backbone of what our alcohol is here. Now we're going to have an O here, an oxygen here, and an oxygen there, and then that will be connected to a nitrogen of a nitro group, right? So we're going to come down here and we're going to put an oxygen there, right? Plus and minus charges on that guy, and we just do this 3 times. So we're going to come over here, put our charges there, and then last this left-handed position with our nitrogen and our oxygen. So this is glycerol. Here we have added 1, 2, 3 nitro groups. So this is known as nitroglycerin. Right now, that is an explosive. Nitroglycerin is very unstable, so little small jolts are going to set this thing off. So we call it shock sensitive. So it's interesting, but when you look at this reaction, if you go ahead and carry out a combustion here, so when this thing explodes, we detonate it, you actually make here 6 moles of nitrogen, 12 moles of carbon monoxide, 18 moles of water, that'll be a vapor, right? It's going to be hot, and then 7 moles of oxygen. So when you add that up all together, you get 35 moles of gas. And that is going to cause this liquid to expand very quickly, right? And detonate. It blows up very fast. Now, one thing that they did to help stabilize nitroglycerin is they added a little bit of basically dirt to it. And with the dirt, it stabilized it quite a bit against that shock sensitivity. So then you had something called dynamite. All right, so interesting little side note. Now, what about this guy over here? So that molecule I want to talk to you guys more about also. So in this polar head group and this nonpolar tail, we can have kind of an organization occurring when we have a solvent like water. So as far as how that molecule will organize in water, let's just do this. Let's just abbreviate here. Just make a bunch of lines here. We're not going to count it up to make sure the number of carbons match the number of carbons up above. All right, so we're going to represent that just by a long squiggly line here with a minus charge at the end. Now that minus charge is going to be the COO minus, right? So that if we have this in a solution of water, water is going to want to solvate around right here. Right? So water likes this part of the molecule, right? But water does not like this part. Okay? So these parts of the molecule are going to gather with each other. So what happens in a solution of water is we get these minus charged groups, and we're going to draw this out like this. And there's better pictures of this. I'll show you guys soon in your textbook. But what we get are these polar head groups here, all hanging out together, and then these tails that are nonpolar all congregating in the middle of this kind of cluster. Now we call this organization a micelle, and you'll learn more about this when you take biochem or if you've taken biology. It's discussed more in chapter 24 of your Wade textbook, which is lipids. So in a water bath, or water is our solvent, you have water hanging out all around here, right? Doesn't matter how many, but a lot of water here. And all these polar groups are going to want to hang out and be near, right, your polar solvent. Right? Now soap is good at dissolving things, because if you have something oily, right, so an oil would be like a long carbon chain. So if you have an oily substance on your hand and you use soap, well, that oil wants to go inside the middle of this molecule, and right, it's basically locked in there like it got stuck in a jail, essentially. So soap is good at dissolving polar and nonpolar substances on surfaces. Now, other thing that I want to point out to you guys here too is that when we look at this structure here, that this structure has a geometry associated with it that you may not have thought much about. So it turns out that what we have here is our carboxylic acid functional group, and then this chain like this, right? So overall, it kind of has a shape that looks like this, right? They're kind of like little pizza slices. Of course, this is exaggerated a little bit, but you can kind of get the idea. So because of this shape, when we add these things together, when they try to form into clusters, you end up getting essentially all these little pizza slices, right? Forming these cyclic kind of structures like this, right? So they want to bend around on each other to form these little micelles. Now, phospholipids, on the other hand, they kind of have the same general principles as having a polar head group and these non-polar tails. So, without drawing the exact structure of a phospholipid, phospholipids look like this. So a phospholipid is a fatty part that has a phosphate group on it. So it's got a PO4 2- head group on it. And it's connected to a CH2, a CH, and another CH2. And then here we have our oxygen, carbonyl, oxygen, carbonyl. And then we're not going to worry about counting that up, but just a long carbon chain there. Okay. Right. Now later on, if we get into chapter 24, we'll talk more about this. So this also has your hydrophilic head group down here, your hydrophobic part. But I want to point out something to you guys here is that this molecule has a little bit, because it has these two alkyl group substituents, it looks more square. Right? So compared to our little pizza shape before, these things have more of a square shape. So when you put them together, they can actually line up and stand up like dominoes a little bit better as compared to like those soap molecules that we saw before when we hydrolyzed the animal fat. So we're going to abbreviate this as a negative charge, but with two tails. Now, what happens is that when these organize with each other, we end up getting, especially in a solution that contains water, right? We end up getting this thing called a phospholipid bilayer. So what that's going to look like, and this is kind of crude, but you can get the idea here, right, is a situation where we have all of these groups hanging out with our minus charges out like this. Now, of course, this continues on, right, and goes that direction too. And then off of here, we just have our little tails hanging out, right, congregating with each other too. So we'll put all those in. Now, on the outside of this, right, on the outer perimeters here, we have water. So that water, again, is what's going to be helping keep those polar head groups all hanging out towards the outside. So out here we have H2O, right, H2O, water on the inside. So this would be maybe extracellular, and intracellular maybe down here below. And the other thing that happens here too is that in these membranes we can get proteins embedded in there. So we have proteins that are all hanging out down here with their tertiary structures. So you have helices, there's some beta pleated sheets, right? It doesn't matter, but just draw in like a bunch of squiggly things here. Okay. Now, proteins are made of amino acids, so let's make a little note down here. Proteins are made of amino acids, and there are various amino acids. Some are nonpolar, and some are polar, some are neutral, some are acidic, some are basic. Now, what keeps that amino acid embedded in the membrane is intermolecular forces. So this part of the protein here, it's not exclusively made of this, but largely made of more nonpolar amino acids, right? Again, it's not exclusively made of them, but because that inner membrane of your phospholipid bilayer is nonpolar, we want to have nonpolar amino acids largely keeping those things and your surface of that enzyme. And then this part up here, because we're in water, is going to have more polar amino acids.